Hi, welcome to the 7th lecture on compactness. Today we are going to prove the continuous image of a compact space or compact set is compact, and we will also look at some applications. In fact, I am going to record this second time because first time when I lectured I forgot to turn on recording. This happens almost once every week. Okay, I have to repeat the lecture again. Okay, anyway, let me go. I have to start. See, you can see, if you don't believe me, you can see all these things. Anyway, so this is as usual the title, the date, and this is my YouTube channel. Okay, if you have any kind of comments and reviews, you can send me to this email ID. You send an email to this email ID. So let us start again. Something which was very interesting going on, now I have to repeat. So let x tau x y tau y be topological spaces, and let f from x tau x to y tau y be continuous. Okay, let k in x be compact, so let it be a compact subset of x. Then what is that I want to prove? This is the theorem we want to prove. We want to prove f of k is compact. Okay, so starting recording is going on. Okay. Yeah, so f of k is a subset of y. I want to prove it's compact. So what should I do? I have to start with an open cover of f of k, and from that I should find a finite subcover. Now remember, f of k is a subset of y. What kind of open covers I should look for? There are type 1 and type 2 open covers. But look at the hypothesis. Hypothesis involves a continuous function from x to y. So continuity of f as a function from x to y I should utilize. Right? So since f is continuous, what do I know? Give me any open set b in x, b in y, then f inverse v is open in x. That's all I know. It's an if and only, right? So what type of open cover should I look for f of k to prove the compactness of f of k? Yeah, I'm sure all of you know. So let us start. Let vi I in I be a type 1 open cover of f of k. So what does that mean? That means for all I, vi is an open subset of y, and what do I know about f of k? It is contained in vi, right? Okay, now from this open cover I have to extract a finite subcover, right? Now what the hypothesis involves two things: k is compact subset of x and f is a continuous function. To exploit the fact k is a compact subset of x, what should I do? I have to somehow construct an open cover of that, right, and extract a finite subcover. I know that I can extract a finite subcover, right? Now think about, from the beginning, in fact even before I introduce compactness, I define open covers and I said how to construct open covers. Okay, textbooks usually don't emphasize that, right? So how will I find an open cover of k? Now I have an open cover vi of f of k, and f is a continuous function, therefore f inverse of vi, that will be open for each I, right? It will be an open set in x. So call it a ui equal to f inverse of vi. So what should I hope? I should hope this ui is an open cover for k. You understand? That's what we are going to do. So let ui equal to f inverse of vi. Remember, what does it mean? X belong to ui if and only if fx belong to vi. Okay, this is a mantra to deal with inverse images, right? Okay, now what do I want to claim? These are all open sets. They belong to top X. Why do they belong to top X? Because F is continuous, VI's are open in Y, right? Now let's look at this UI as I varies over Y. What do I want to claim? I want to claim this is a type 1 open cover of K. Yeah, what does that mean? That means I know this is an open set. These are all open sets in X, all of them. Therefore, I only have to prove K is a subset of union I and I of UI. Okay, this is all I have to prove. Yeah, so let us do that. So let us start with any X in K, then that implies Fx is in Fk, right? But Fk is contained in union I and I of Vi. Okay, so what does this imply? This implies there is a J in I such that Fx belong to Vj, right? But this is same as saying there is a J in I such that X belong to F inverse of Vj. But what is Vj? It is Uj. Therefore, what do you think I have proved? Given any X in K, there is a J in I such that X belong to Uj. That means K is a subset of union Ui I in I. Because give me any X, it belongs to union Ui. I should prove that X is J such that X belongs to Uj. That's all I prove. Yeah. Therefore, Ui I in I is a type 1 cover for K. Right? So pause, review, proceed. Now what do I know about K? K is compact. Okay, therefore there exists a finite subset F of I so that K is contained in union Ui I in F. Yeah, if you want to have a look at the picture, so this is my X, this is my F, this is my Y. Okay, this is my K compact, this is maybe my F of K. So what am I given? I am given open cover of F of K. These are my VIs. So I have open covers of K and so on. These are my UIs, right? So finally many of them are covered, right? So what is that I should guess now? My guess is Vi I in F is a finite subcover F of K. This okay, this is what I have to check. Okay, then I will be through, right? So if that, what does it mean? I have to, that is I have to prove F of K is a subset of union Vi I in F. This is all I have to prove. Yeah, so let us start with the Y in Fk. Then what should I do? I have to check whether there is a J in I so that Y belong to Vj, because it has to be in the union on the right side. That means there is a J. Keep all these things in mind. I'm going very slow, right? Now Y belong to Fk. What does it mean? There is an X in K so that Y equal to Fx. Yeah, so I start with a y here. Okay, therefore there exists some x such that y equal to fx. Now this x has to be in one of the ui's where the I comes from f, right? Since k is contained in union ui, I is in f, okay, there is a j in f so that x belong to uj. Yeah, very good. Now x belong to uj, but what is uj? F inverse of bj, my u and u. Okay, this is if and only if fx, yeah, this is uj. Let me just make sure, because even I got confused what was the what I have written. Yeah, that means fx belong to bj, but that is nothing other than y belong to bj. So have I proved it? There is a j so that, oh sorry, there is, yeah, there is a j so that y belong to bj. Have I proved it? Yeah, that done. Therefore what do you think I have proved? I have proved that Vj, J and F is a finite subcover. Okay. Therefore you gave me an open cover of f of k of type 1 in Y, then I was able to find a finite subcover. Therefore f of k is compact. Therefore what is the conclusion? Conclusion is f of k is compact. So pause, review, proceed. Yeah, so let us look at some applications. Okay, number one, this is the most general application. Suppose x tau is compact space and yd a metric space. Let f from x to y be continuous function. Right? Now by the last theorem I know f of x in y is a compact subset. But remember, we already know if a is a compact subset of y, this is a fact we know. If a is a compact subset of y, that means a is closed and bounded. Yeah, so I'm going to make use of that. All right, therefore what do I know? Therefore f of x is in particular bounded. Of course it's also closed in y. Okay, now an immediate application of this is, suppose f is from x tau, this is a compact space, to R, and now y is a metric space, but that y is real numbers with the usual topology, right? So then what do I know? Then f of x is a compact subset of R. Right? Therefore that means this is closed and bounded in R. Right? Since it's closed, sorry, since it's bounded, this is a bounded subset of R, it's non-empty, therefore its LUB or GL, the supremum exists, that is LUB of fx as x varies over capital X. This is the supremum of the set fx exists. Where? In R. Right? That is the LUB property of real number system. And similarly, the GLB, which is the infimum of fx, exists in R. Right? Now what I want to claim is, this is a claim, m belong to f of x, and similarly little m belong to f of x. No, what does this really mean? Try to understand. That means there exists an x1 so that f of x1 equal to capital M. There is an x2 in capital X so that f of x2 equal to little m. Do you understand that? Yeah? Okay. So let us take a digression. This is actually something to the real number system now. Okay. Suppose a subset of R is closed and bounded, non-empty of course. Okay, by the least upper bound property, LUB of A exists. Then I claim alpha actually is an element of A. Right? The LUB need not be an element of A, but just because it happens to be closed, it's an element of A. How do I prove that? Do you remember? How do I make use of the fact LUB property of a number? If alpha is the LUB of A, then you give me any beta less than alpha, then beta is not an upper bound of A because it's less than alpha, right? Therefore there exists an A in A such that beta is less than A, that A of course will be less than or equal to alpha. Okay, remember this is the mantra of using LUB. Okay, these are the thing. If you learn this, you will be very happy with that. Okay, now what I want to do, I want to look at alpha minus 1 upon n. This is strictly less than alpha, therefore this is not an upper bound. Yeah, that means there exists A, I call it AN, okay, because for each n I am going to consider alpha minus 1, therefore there will exist an element A. That element may depend upon my choice of n, therefore I call it AN. Okay, so that what happens, alpha minus 1 by n is strictly less than AN, but that AN is less than or equal to alpha because alpha is an upper bound. Right? Now whenever you see this chain of inequalities in real analysis, what should you think of? You should think of sandwich lemma. Sometimes they also call it squeezing theorem or some such thing. I don't know. Okay, now this sequence alpha minus 1 upon n converges to alpha. This is a constant sequence that converges to alpha. Therefore, the middle sequence AN also converges to alpha. That's what it says. Right? Now, what do I know? AN is a sequence in where? In the set A. And AN converges to alpha. Now, you should again recall two statements. Maybe I will write it. Okay, we have to recall two statements from general thing. What is that? If suppose XD is a metric space, right, and then X in A, okay, A is a subset of X, non-empty subset. X in X is an adherent point of A if and only if there is a sequence AN in A so that AN converges to X. Okay, in my topology course I had already done. If you watch my videos on metric space also, I have proved this. Right? And second fact is, again, okay, this is in any topology space, X tau and A is a subset of X, then X and X is assume this is closed subset, right? Or let me say A is a subset of X. Okay, then A is closed if and only if, okay, every adherent point X in capital X lies actually in A. Right? Pause, review, proceed. Please try to, if in case you have forgotten, please stop, revise these two statements. Now come back. So I have fx, right? This is a compact subset of R, therefore it's closed and bounded. And my M is the LUB of this set, right? Now, since M is the LUB of this set and this set is closed and bounded, I know M has to be in f of x, right? By, yeah, you follow that? What does that mean? That means there exists an x1 in x such that M equal to f of x1, right? Now start with any x in capital X. Now what do I know about fx? That is less than or equal to M, because M is the least upper bound, right? But this M is f of x1. Therefore what do I get? For every x, f of x is less than or equal to f of x1. So what does it mean? X1 is a point of maximum. Right? So this is what you say. And similarly, you can work with M. There is an x2 in x, so that M equal to fx2, and hence for all x in capital X, M equal to infimum of fx. Okay, that is a right. Therefore it's less than or equal to this is fx1, fx2. Therefore x2 is a minimum. Right? So this is what you loosely say. What do you say? That any continuous real valued function on a compact space attains its maxima and minima. Yeah, those of you who have followed my earlier lectures, I think in the second or third lecture I proved this without any of these things, simply by constructing an open cover and using the property of LUB GLB there also. Okay, so this is the standard proof you will find in any book. Okay, the above proof is the standard proof found in any book. But we have given a different elementary proof in compactness 3, if I remember right. So compare these two things. If you want to master the subject, okay, just because you think that you had already watched, it's okay, don't do that. See, whenever I do, then I go through the proof again, go through this proof also, try to compare, so that both the proofs becomes crystal clear. Okay, this is the way to master the subject, not simply going through, I had understood it once, so I don't have to worry about it. That's not the attitude. If you want to master, you should revise. Okay. Okay. Now, before I close the lecture, let me look at. We had already seen the following thing: 0 to pi open to the circle, which is xy in R2, so that x squared plus y squared equal to 1. Okay, right? Now this one is compact. How it's compact, that we have seen, because let us look at 0 to pi to S1. This is a subset of R2. Okay, the map is t going to cos t sin t. This is a continuous function, and this we know is a compact set in R, is a compact subset of R. therefore its image, okay, f of 0 to pi is S1. Therefore this is compact subset of R2. Okay, right. Now restrict this f to only this function, this domain, okay, namely t going to cos t sin t, right? Look at this function. Oh, this function is continuous, right? And what is the image? Image is again S1. Do all of you agree with that? Yeah. And this function is one, this, therefore this function f is onto. Yeah, because given any vector x comma y such that x squared plus y squared equal to 1, then you know there is a unique theta between 0 and 2 pi, okay, but any theta, so if you say, are you following, there is a theta in R such that x equal to cos theta and y equal to sin theta, and if theta 1 and theta 2 both have the same thing, x equal to cos theta 1, y equal to sin theta 2, then theta 1 minus theta 2 is a multiple of 2 pi. These are the facts of trigonometric functions, right? Therefore the interval 0 closed open at 2 pi maps onto the circle, and for the same reason f is also 1 1 on the set 0 to 2 pi, because what does it mean? It says that suppose cos theta 1 sin theta 1 equal to cos theta 2 sin theta 2, right? Then what do I know? Cos theta 1 and sin theta, cos theta 1 equal to cos theta 2. That means theta 1 and theta 2 differ by what? Because sin theta 1 is also sin theta 2. Therefore this means theta 1 minus theta 2 is a multiple of 2 pi. If I assume that my theta 1 is greater than theta 2, this is positive. Therefore I can n has to be greater than or equal to 1. But remember, theta 1, theta 2, where they are? Theta 1, theta 2 are in 0 to 2 pi. And therefore, theta 1 minus theta 2 will be strictly less than 2 pi. Assuming they are not equal, it will be strictly less than 2 pi. But this will be greater than or equal to 2 pi. So this contradiction shows this function is 1, 1. Okay, please pause, review, proceed. Therefore, my function from 0 to pi to S1 is 1, 1, continuous, 1 and 1, 1 and on to. That is a continuous bijection. But f is not a homeomorphism. Because if f is a homeomorphism, what does it mean? F inverse from S1 to 0 to pi, it must be again continuous bijection. If not, this f inverse exists, it should be a continuous bijection. That's a definition of homeomorphism. F of f inverse both are continuous. F must be bijection, and f inverse both are continuous, right? Therefore, if f were a homeomorphism, then f inverse will be continuous bijection. But then what is the image of f inverse of S1? That is 0 to 2 pi. But this is a subset of R, and this is not compact. But you have shown this is compact. Yeah? You follow that? Right? Right. Why this is not compact? We have just now shown that any Borel theorem we have seen, but anyway, we have seen that in any metric space, if a set has to be compact, it has to be closed and bounded. This one is bounded, of course, but it's not closed. Therefore, this cannot be compact. This is closed, but not compact, but not bounded. Sorry. Bounded, but not closed. Therefore, not compact. Okay, right? Therefore, not all not all continuous bijections are homeomorphisms. That is what you have to learn. So, what is the moral? Yeah. So there is some reason. If you had followed my lectures on continuity on topological spaces, when I talked about homeomorphism, I said very carefully. See, whenever x and y have some mathematical structure, similar mathematical structures, that is maybe both are groups, both are vector spaces, both are rings, or both are topological spaces, then I say a bijection x to y, okay, is an isomorphism. That's a general word I use. If both f and f inverse are homomorphism. If x and y are groups, I want to say f and f inverse must be homomorphism. It must be a bijection so that f and f inverse are homomorphism. Similarly, if it's x and y are vector spaces, f and f inverse must be linear maps. Of course, f must be bijective. And if x and y are topological spaces, what do I want? F must be a bijection so that f and f inverse must be continuous. Right? I insisted on that. Whereas in the case of algebra, okay, if I have a bijection f from x to y, which is also homomorphism, then f inverse is a homomorphism of y to x. That is free. You understand that? This is a subtle difference. So algebra textbooks do not insist to define isomorphism the way I would like. I would like f as well as f must be a bijection first, and f inverse both must be homomorphisms. Homomorphisms in that particular context. In the case of continuous, so in the case of topological spaces, homomorphism means continuous for me. In the case of groups, it should be group homomorphism. In the case of vector spaces, homomorphism is linear map. And in the case of two rings with identity, I would like to be ring homomorphism, and so on and so forth. Okay, you get the gist? Okay, let us stop. Please go through this. There are a lot of small things which are never you explain in the regular course, because usually when you look at a textbook, the textbooks assume that the student had gone through BSc and first year MSc, possibly at least one semester of MSc, so you should have background. But unfortunately, in our system, should I say, it's not necessarily true. That's a very sad state. That is why I take a lot of pains to explain even the smallest details like set theory, real analysis, various things. Okay, and don't worry, you learn all these things, you can master. Okay, I wish you all the best. We will meet again.